I need to start these videos with another word than okay. Okay, so the old formula for gravitational potential energy is this. Ooh. What's wrong with this? Well, it makes a few assumptions, all right? One of them is that G doesn't vary above the surface of the Earth. And there's also an arbitrary datum, a reference height, that measures the height from, saying that the gravitational potential energy at the surface of the Earth is zero, which is not the case. Anyways, we're going to start off talking about gravitational potential energy here with the definition of work energy theorem, basically that the work done on the system is equal to the energy added to it. What this tells us, all right, when we're dealing with transferring energy between gravitational potential and kinetic, all right, anytime you're putting work into a system, it's path independent, which means it doesn't matter what path you take between 2 points, right? The work done moving that object between those 2 points on any path is the same. And the reason is that gravity is a conservative force. Okay, if you were doing work against friction, that is path dependent because you are not able to recuperate the energy that you've lost as you move it along different parts of the path. So the change in gravitational potential energy is zero between any 2 points at the same height, right? And it's zero for a closed path. In other words, if you start and end at the same place. So when we start talking about gravitational potential energy, the definition that we should use is that it is the work done in bringing a small mass in from infinity means of calculus, say, to a point in a gravitational field. So the base level here is that gravitational potential energy equals zero at the point infinity away, right? In other words, at r is equal to infinity. The consequence for this, right, is that the gravitational potential energy, in other words, what that's saying is that gravity has absolutely no influence over the object when it is an infinite distance away. The gravitational potential energy, therefore, is negative as a result of this. And the reason for that is that if we start at infinity, all right, and bring a small mass in from infinity, okay, we have to do negative work. We have to remove energy from the system because gravity is an attractive force, right? So we're doing work against gravity. We're doing negative work. So U is negative for any finite separation. And so the image I want you to have in your head is we have this small mass. It's at infinity. We bring it all the way in to some point here, okay? And at this separation right here, this is our R, excuse me, okay? And actually, use the capital R here. And for those of you who know calculus, the work done in any system is the integral, all right, of force with respect to position. So what we do, we bring it in from infinity to a position R. This integral, guess which force we're replacing in here? Yep, working against gravity. And over R squared dr. Okay, so this is equal to negative g bn little m all over r, infinity to r is where we're evaluating it, and this is equal to, therefore, this quantity. So this is, due to the work energy theorem, okay, all the work we're doing is being put into gravitational potential. So our new formula for gravitational potential energy is U is equal to negative g big N times little n all over wherever we are, that's separated from the other object. So the unit for this is joules. It is a scalar, where energy is a scalar. So if we sketch a graph of the gravitational potential energy of an object versus its distance from the center of the planet, it's going to look something like this. It's in the fourth quadrant here. And we'll say that the radius of the Earth is somewhere here. Okay. It's going to be something like this. All right. There we go. Quick little example. What's the gravitational potential energy of a 5,000 kilogram satellite? Let's take our equation, the new formulation that we have, substituting our values. We end up with this. Negative here. This is all over. And that distance is the distance from the center to the surface of the Earth, and the average distance, okay? When we calculate this here, we end up with negative 3.13 times 10 to the 11 joules. And if we do the same thing, except now our R is equal to 6.57 times 10 to the 6 meters. That's adding those 200 kilometers, right? Work out the prefixes in orders of 10 on your own. The new gravitational potential energy is equal to negative 3.04 times 10 to 11 joules. All right. So the next question asks, how much does the potential energy of the satellite increase or decrease when it is put into orbit? All right, so that's a delta U. So it's U. So the final gravitational potential energy minus initial gravitational potential energy. And when you do that, you have an increase of gravitational potential energy. Right. 9.53 times 10 to the 9. Now, I should actually say this. Right. That is going to be an increase of gravitational potential energy, I believe. What do you think about this? Yeah, that's right. What I said, it took me, I paused it there and thought about it, but it's an increase in potential energy there. So the thing is that whenever you solve for the change, that will tell you whether or not you have an increase or decrease, and that's what's physically meaningful. Right? So the next question here is, what is the amount of kinetic energy needed to put the satellite into orbit? All right, and the amount of kinetic energy needed is the change in energy of the system, change in potential energy. All right, so if we are to assume, all right, the change in energy of the system, let's see here, that our change in gravitational potential, right, is going to have to be equal to whatever kinetic energy we put into it, change in K, all right, and this would be equal to this number of joules. Okay, why is this considered to be the minimum amount of kinetic energy needed to put the satellite into orbit? Well, conservation of energy. The kinetic energy has to go somewhere and it's being put into the gravity.